Today, we shall discuss the concept of center of mass, right? So let us write center of mass. Now, uh, to start with, let me tell you, this concept of center of mass is a very important concept in physics, though it is not very commonly necessary for uh, lower level or school level students, but the concept is a very important concept. I want to first explain to you what is the concept really. To start with, let us consider that, uh, let us say you are here. Let us say you are here and a long, long distance away from you, pair of stars. It's a pair of anybody, but let's say it's a pair of stars. Maybe wherever you see them, this pair in the eastern sky or western sky, they appear to be in the same distance, and it always is a couple or is a pair. And mind it, this could be not only two, it could be a cluster of such heavenly bodies, cluster of such stars. To make the matter simple, let us consider there are only two of them. Now, let us say you are a student of astronomy. Now, you want to measure or do some experiment on the behavior of this pair. Then, if you have to consider a combined mass of the pair, obviously combined mass will be M1 plus M2. There is no doubt in that because we know what mass is. What is the location of M1 of M2? The combined mass is capital M. Then where is capital M? The capital M is here or here or here, where it is. If M1 and M2 are same, identical, then of course the location of capital M is just in between the two. But they are not same. If the two masses are not same, then where is the location? That location, whatever is the location, say this is the location, that location can be called the center of mass of the combined mass, capital M. This is roughly what is center of mass, right? Now, we shall go into a little bit more detail of it step by step. Let us first find out the center of mass of two items, center of mass of two items, and their combined mass is M1 plus M2. But let's find out what is the location of this mass. Let us consider this is to make the matter very simple, we consider first the two masses M1 and M2. M1, this is the mass, this is the position A, mass M1, and position B, mass. And M1 and M2 are not equal. If they are equal, obviously the center of mass is just in between, just in the middle of the two. Then let us consider this is the x-axis. To make the matter simple, we first consider that both of them lie on the x-axis, and this is the origin, right? Then total mass M is of course is capital M is of course equal to M1 plus M2. There is no doubt in this. And let us consider that the center of mass is somewhere here at a distance of x from here. And let us consider the distance between A and B is d. That case, by the concept of the center of mass, the distance OA, that multiplied by M1, OA multiplied by M1 plus distance OB multiplied by M2. Let us say this point is P, will be equal to OP multiplied by 10M. Then only the concept of center of mass applies. Because two masses separately, M1 is at A, M2 is at B, and we consider both of them together is at capital M. Now, and this capital M is equal to M1 plus M2. So let us write M1 plus M2. Now, OA M1 remains same as OA into M1 plus OB is OA plus D. So this is also OA into M2 E into A. So here we have OA multiplied by M1 plus M2. Therefore, OA multiplied by M1 plus M plus distance D multiplied by M2 times OP multiplied capital M. Right? Now, M1 plus M2 is capital M. So, OA capital M plus D into M2 is equal to OP into capital M. Here we find that OP minus OA capital M is OP minus OA into capital M is equal to DM2. From here, what do you find? OP minus OA is the X. So, X capital M is equal to, therefore, X is equal to D by capital M, where capital M is M1 plus M. This indicates that distance of the center of mass from M1 is dm2 by capital M. Similarly, you can find out distance of the center of mass from M2 will be dm1 by capital M. So this is the basic concept of center of mass. Next step, we go to the next step where we go to the next step And this is the only two masses. In the next step, what do we consider? Let us consider a three-dimensional space, right? Let us say this is x-axis, this is y-axis, and let's say this is z-axis. And let us consider that there are many discrete masses. There are many discrete masses. And we want to find out, obviously here also, and discrete masses are like this. Let us consider that the mass M1 is located at x1, y1. Say mass M2 is located at x2, y2. Similarly, it goes on. Let's take a general case. Mass Mi is located at xi, yi. Again, it goes serially, it goes. Let's say the last one is Mn. Let us say there are capital N number of such masses is located at x capital N, y capital N. Now here, if this is say a cluster of stars far away from us, or a cluster of anything, and they always move together. So whenever we have to deal them in physics, we can always combine them, a combined body, but of discrete masses. So total mass of all of them, of course, will be equal to capital M is equal to sum of all masses. Capital M is equal to sum of all masses, Mi, and the summation is over I. I is equal to, you can consider, right? This way, I is equal to from 1 to capital N. Now here, let us say, I do not know where its center of mass will be. Let us say its center of mass is somewhere here. Let us say its center of mass is somewhere here, and which has a coordinate of, say, which has a coordinate of capital X, capital Y, capital Z. Then, considering the x-axis only, like we have done in earlier cases, the effect of total mass capital M located at capital X, that means we can write this word, total mass capital M located at X is equal to discrete sum of all of this Mi, Xi, I equal to I from 1 to capital N. Similarly, My, this way we can find the value of X. What is the X? And My will be once again the discrete summation of Mi, Yi over I from is equal to 1 to N. And similarly, Mz will be equal to discrete summation of from I is equal to 1 to capital N of Mi and Zi. From these three equations, we can find out the values of X, Y, Z. That means if there is a discrete cluster of discrete masses, then their center of mass location, capital X, Y, Z, is given by this equation. Step. Consider that this masses is not discrete. Let us say it's a continuous mass. Similarly, let us say this is the x-axis, this is the y-axis, and this is the axis. And let us consider there is a mass, irregular shape mass like this. So obviously here, this discrete summation formula will be replaced by the integral equation. They are in the same fashion, our mx, m capital X will be equal to integration of from, say, this is x1 and this is x2, from x1 to say x2 or say xn, capital I write capital xn to make it simple. x1 to xn, the mass m, which has to be found out as a function of x into dx. Similarly, my is equal to y1 to y2 my, that means mass as a function of y, dy. And similarly, z is given by integration of z1 to zn. This was y. Mass as a function of z, my integration with respect to dz. These are the three. This is the basic concept of center of mass. So at the end, what we find that center of mass is nothing but that particular point where the mass of a extended body can be considered located at a particular point. So far, in kinematics, etc., we have solved many numerical problems where we have seen a boy throws a ball upward. Mind it, the ball is not a point. The ball is an extended body. Similarly, everything in this world is an extended body. But we have solved all these numerical problems considering it is a point. Now, of course, so the theoretically, this is a extended body. All bodies are extended bodies. And here, to give a rough idea, where is the center of mass? Let's take some examples. Suppose it's a ball. It's a ball. Not a solid ball. Any cricket ball, it's not a solid. Its center of mass is, of course, at the center, at a geometric center, considering the ball is regular and homogeneous. Regular means its shape is exactly a sphere. Homogeneous means its density is same everywhere. If it is a square object, obviously it is at the center. If it is a triangle, obviously center of mass is C. If it is a three-dimensional box, obviously the center of mass is somewhere here where the corner diagonals meet together. So that is how we solve, we go on solving these problems. That means whenever we are solving any problem of physics, we consider the mass is a point mass. So it is actually, physically, it is not a point mass. But in higher physics, when you will have discrete masses like this or an irregular object like this, you will have to calculate and find out the center of mass. Now let us make a few calculations how to find out the center of mass. To start with, let us consider there is a there is a straight rod. There is a straight rod. We consider the thickness of the rod is very, very small with respect to its rate. And let us consider this rod, is lies on the x-axis. This is the rod. Want to find out its center of mass. Let us consider this is a straight rod, straight and thin, straight and thin rod. If it is a wide rod, and if you place the rod such a way that the center line of the rod lies on the x-axis, of course, the capital Y, that is Y axis of the center of mass, will be on the x-axis. Anyway, here, let us consider the mass of the rod, mass of the rod is equal to M. And length of the rod is equal to capital L. Then mass per unit length, mass per length equal to capital N by L. Right? Now what do we do? Consider a small part of the rod of length dx at a distance x from the origin. Right? At a distance x from the origin. Then what is the mass of the length dx? So, mass of the whole piece of rod of length dx is equal to m by L dx, because mass per unit length is m upon L, right? Then we want to find out m capital X. We know by the equation m capital X is equal to integration of m dx, right? Integration of, you said, in m dx. Now, the x has to be integrated from 0 to capital L. The length of the rod is L, 0 to capital L. And this small mass, is m upon L dx. So this is equal to L x into m upon L dx. This is equal to this capital M and capital L will come outside, m by L, integration of 0 to capital L of x dx. This is equal to m upon capital L, and integration of x is x square by 2, and limits are 0 to this is equal to m by capital L. This is L square by 2. L square by 2. right? Now this L and L square gets cancelled. What we have? L remain. So this is equal to ml by 2. So mx, therefore, mx equal to ml by 2. Therefore, x is equal to L by 2. That means center of mass is at a distance of L by 2. This is, of course, we can do this, we can think of this without all these integration calculation. If it is a homogeneous rod of uniform thickness, then of course its center of mass will be L by 2. But if it is not a homogeneous mass, or if it is not an irregular mass, let us say the size of the rod it is not a rod, it is something like this. Then of course this integration will create a different result. Right. Next, we shall take another example. We shall take another example. We shall take example of a thin semicircular rod. If it is a circular rod like this, then obviously its center of mass is here. Any calculation for this we can say without even looking at it. Its center of mass will be here at the center. Although, mind it, although there is no mass at the center, but the theoretical center of mass is at the center. Now we are trying to calculate the center of mass of a semicircular thin wire. That is interesting. Let us say we have got a semicircular thin wire like this. It is its center of mass. To calculate its center of mass, consider the y-axis is here and x-axis is here. And so this is the origin. Then what do we do? We take any point on this thin rod at an angle theta. At an angle theta. And we consider a small, differentially small part of this rod, of this semicircular rod, an angle d theta at the center. Looking at angle d theta at the center. And if r is the radius of this semicircle, then of course this length is r d theta. You know, where theta is measured in radian. Right? Now, what is the xy coordinate of this point? This point xy coordinate, x is r cos theta, and y is r. So this side is r sine theta, and this distance is r cos theta. Right. So similarly, once again, let us draw a line here. This was the earlier problem. This problem is a thin semicircular wire. Trying to find out its center of mass. Now we consider, now what is the length of this? length of this, is, of course, pi r. And if its mass is m, mass is equal to capital M, then mass per unit length, mass per unit length is equal to m upon m r. Now, what is the mass of this small part? So, mass of the small section, the length of the small section is r d theta, and mass per unit length is capital M by pi r. So, this is equal to m by pi r into r d theta. And mass of this small section, we can consider this as dm. This is a mathematical expression. So what we find, dm is equal to Lm upon pi d theta. This is the main part of this reduction. Then we have to just integrate this. Now, going by the basic principle once again, mx, if capital X be the x-axis dimension of the center of mass, is equal to x integration of x dm. Now here, the x, this x is r cos theta. So r cos theta multiplied by dm is m by pi d theta, capital M by pi d theta. And if the parameter is theta, here we find it, we are on d theta. Then obviously it has to be integrated of theta from 0 to pi. 0, pi. 0 to pi. So here Rm by pi will come outside. Rm by pi will come outside. The integration of cos theta d theta from 0 to pi. Rm by pi, and integration of cos theta is sin theta from 0 to pi. Now sin pi is equal to 0, sin 0 is equal to 0, so this is equal to, if capital M is multiplied by x is 0, therefore we can write capital X is equal to 0. That means the center of mass lies on the x-axis. Let us write it. So the center of mass lies on x-axis. But obviously, we have to find out where is the center of mass in the y direction. If we do the same thing in y direction, then in y is equal to integration y dn is equal to, now y dimension is r sin theta. R and theta. dm is, we have found, capital M upon pi d theta integration from 0 to pi as usual. Similarly, r, m, and pi will come outside. R, m, and pi will come outside. Integration of 0 to pi sine theta. Integration of sine theta is minus cos theta. R, m, and pi. Integration of sine theta is minus cos theta from 0 to pi. This is equal to r m by pi, and cos of pi minus, and cos pi is minus 1. So this becomes plus 1. And then this is a minus sign. So it will become another plus, and cos 0 is 1. So this becomes 2. So this is equal to 2 Rm by pi. So capital M y is 2 Rm by pi. Therefore, y is equal to 2 R by pi. That means the center of mass is at x is 0, 0, comma 2 R by pi. This is where the center of mass of this thin rod is. The 2R by pi, if you try to estimate 2R by pi, I think will be somewhere here, somewhere here. 2R. So this is the center of mass of a thin semicircular rod. We shall take another attempt to find out the center of mass of a semicircular thin sheet. Let's say a semicircular thin sheet of metal, right? It may be like this. A semicircular thin sheet. Let's say it's a semicircular thin sheet. A semicircular thin sheet like this, right? It's a semicircular thin sheet. Here, once again, we consider the center of the semicircle as the origin. This is y-axis and this is x-axis. And also, it is given that the radius of the semicircle is capital R, and total mass is equal to capital M. Let us draw a line here so that two things don't get mixed up. Total mass is capital M. Now, in the last problem, we found out the mass per unit length. Here we shall find out the mass per unit area. What is the area of the plate? Area of the plate. Area of the plate by r square by area of the plate is pi r square by 3. Because area of the total circle is pi d square by 4. So pi r square by 2. So mass per area is equal to is capital M divided by r square by 2. This is equal to M by pi r square. This is mass per unit area. right? Then what do you do? We adapt once again the technique of differential calculus. Take a, consider a thin, very thin semicircle of radius small r. Radius of the total total semicircular plate is capital A. But we consider a thin, very thin semicircular ring, we can say, of small r, and the thickness of the ring is dr. Thickness of the ring is dr. That means inner radius of the ring is smaller, outer radius of the ring is smaller plus d smaller, right? Now, what is the length of this small ring or length of this hypothetical ring? Length of semicircular ring. I should not say ring because ring is a circular, say semicircular section, you can write. Length of the semicircular section is pi r, pi smaller. And what is the area of this semicircular section? Area of this section pi smaller is the total length of the semicircle, and we have considered it has a thickness of dr, so pi smaller dr. This is the total area of this thin section. And we have earlier found the mass per unit area is 2 capital M by pi r square. So what is the mass of this small area? So mass of in semicircular section is equal to pi r dr pi small r dr multiplied by 2m by pi capital R square. This pi and pi gets cancelled. So its mass we find is m by capital R square, 2m upon capital R square multiplied by R dr. Now we are ready for integration. Now we are ready for integration. And what we have already arrived at is that dn is given by this expression 2m by capital R square multiplied by small r dr. Mind it, remember once again, capital R is the radius of the semicircular plate and small r is only the radius of the thin semicircular section that we have assumed or imagined for the purpose of our calculation. Now, remember that a little bit ago, we have determined here, we have determined the center of mass of a thin semicircular wire, and we determined its y coordinate was at 2r by pi, right? You remember this? 2r by pi, where capital R was the radius of the semicircular wire. But now, the radius of the semicircular wire is smaller. So, keeping that in mind, now we can start the integration. Obviously, center of mass will be somewhere on this line on the y-axis. So we will not do any integration, etc., for to find out the x ordinate. So x ordinate, let me write out this way. X ordinate of the center of mass is x equal to 0, since the body symmetrical over y-axis. So half of the differentiation, etc., we ignore, because we know it will be on the x ordinate will be. So y ordinate we do not know. Y ordinate we should find out. So we use the equation my, where y is the ordinate of the center of mass. My equal to integration of y dm. Now here we are working on this particular semicircular ring. And the center of mass of this particular semicircular ring is already given 2 into radius by pi. So here I write the ordinate of the center of mass of the thin semicircle equal to 2 small r by pi. That in mind, keeping that in mind, my will be equal to integration of 2 smaller upon pi into dm. And what is dm? Dm is given by this. So this is equal to integration of 2 smaller upon pi multiplied by 2 capital M by capital R square multiplied by small r dr. Now we are integrating over dr. So we have to find out the limit of small r. Limit of small r is from 0 to capital R. This is very clear. 0 to capital. So this is equal to, we have 4 2s are to 4 capital M, 4 capital M pi capital R square. You can take outside. What remains inside is this small r into small r. So small r square dr to be integrated from 0 to capital R is equal to 4 capital M by pi capital R square. Integration of R square is R cubed by 3, and limit is 0 to capital R. So this is equal to 4 M by R square multiplied by capital R cubed by 3. Right? So this R square and R cube makes R here only. So this is equal to 4 M R by 3 pi. So the center of mass is at, let us write it down, to conclude, so the center of mass is at that 0, comma 4 m 4 m, sorry, 4 0, comma 4 m capital R by Q pi. So these are the one or two very thin or very small examples we have seen in to give a clear idea or concept of what is center of mass. And if we are forced to find out the center of mass of an object, how to proceed, right? As I said, that this center of mass is not very common in physics problems, at least in school level, but the concept is very useful at higher level of physics. So you should know what is center of mass, right? Next, we shall go to next chapter next day.